Hello and welcome to today's class. Alright, so in the previous video, we've talked about Miller indices, how to draw the positive planes and how to draw the negative planes and determine their directions as well. In that video, I also give about the formula for calculating the interplanar distances between two planes. I also give about the formula to calculate the angle between a plane or a direction. So let's consider this question, okay, on the board. The first question says, draw the plane and direction of the following FCC structure with Miller indices of 110 and 102. And the second question says find the interplanar distance between the two planes of Miller indices 321 and 102 in a unit cell with lattice constant parameter of 4.05 Armstrong and find the angle between the directions 321 and 102. So let's start with the first question. First question is asking us to draw the direction and planes of 110 and 102 Miller indices. So let's start with the first question. So we are given the Miller indices. So I will do the both of them in pari passu. We are given the Miller indices to be 110 and of course 102. So we have to draw these given structures. All right. So the first thing, like I said, is to find the intercepts. Okay, find the intercepts of planes. All right, that becomes the first thing to do. So for the first plane, okay, so I will do them side by side. I will do them side by side for the first plane and for the second plane. The first Miller index is at 110, while the second Miller index is at 102. So I will do them all together. Okay, so let me highlight this as this. All right, the x-intercept, remember, is equal to 1 all over h. This stands for the h, this stands for k, and this stands for l. Okay, in the Miller index, this also stands for h, this stands for k, and this stands for l. So x-intercept is 1 over h, which is equal to h on this plane is 1 here. So this becomes 1 all over 1, which is equal to 1. This implies that the x-intercept here is equal to 1. Whereas for this other plane, the x-intercept is also 1 over h, and h is 1 here, is simply 1 all over 1, which implies that x is also equal to 1. The y-intercept on this other Miller index is 1 all over k, and from here we have k also to be 1, so this is simply 1 all over 1, which is equal to 1. So this implies that the y-intercept on this plane is 1. Also the y-intercept here also 1 over k, and k is 0 here, it becomes 1 all over 0, which is infinity. So this implies that the y-intercept on this plane is at infinity. And finally the z-intercept, the z-intercept is 1 all over L, and L is here 0, so you have 1 all over 0, which is infinity. So this simply implies that the z-intercept for this plane is actually at infinity. So I have it to be at infinity. And finally, the z-intercept on this other plane is equal to 1 over L, and L here is 2, so I have 1 all over 2. All right, so this simply implies that z is actually 1 all over 2. So in general, the plane I'm drawing for this Miller index, my plane becomes what? X is 1, this is 1, y-intercept is 1, 1, and z-intercept is infinity, becomes infinity. So this becomes my plane, and of course, the plane I'm drawing here, x-intercept here is 1, so you put it down 1, and your y-intercept here is infinity. I have my infinity, and the z-intercept here is 1 all over 2. So this becomes the plane which I am going to be drawing for these two structures. Okay, so I'm going to shift the camera a bit now. All right, so let me plot these two planes here. So I will draw my first structure. Okay, I'll draw my first structure. Okay, let me draw my first structure. Okay, I'm going to make it smaller because I need to create space for myself over here. Okay, so this is my y-intercept, this is my x-intercept, and this is my positive z-intercept. I have this. So I'll draw the second structure for the second plane. Okay, I'm going to be doing them jointly. So this is my z-intercept, this is my y-intercept, and this is my x-intercept. So for the first plane, we are to plot 1, 1, x. 1, 1, infinity. So this is my x-intercept, this is my y-intercept, and this is my z-intercept. The x-intercept is at 1. So remember, this is all a unit cell, so which means their distances apart are what? Equal, and they are all 1, 1 apart. All right, so my x is at 1. From the origin, this is x, so we have here at 1. Okay, so this is my x at 1. The next, my intercept on y is also 1. From the origin, this is y, so I have this intercept to be at 1. That means for the z, it is at infinity, which means it does not exist. So there is no intercept on the z. So we plot these points, join y and x together, we have this. But not also forgetting, I can also call here my origin. If here is my origin, my x-intercept is 1. So simply trace, this is 1 on the x, and this is the x-axis, which is 1. My y-intercept is also 1, which is 1 here, and this is 1. Therefore, join the x and the y together. Okay, join the x and the y together. All right, so I have this. Okay, so from this point, this plane is the plane which we are talking about. So this becomes my 1, 1, 0 plane, or simply my 1, 1, infinity plane. So I can write here 1, 1, 0 plane. Okay, the next question says we should find our direction. Remember, the direction is simply a line drawn from the origin which cuts the plane at 90 degrees. So if I draw a line from this origin to cut this plane at 90 degrees at any point, this becomes my direction. So enclose it in a square bracket, 1, 1, 0. That becomes the answer to that question. The next says we should plot the 1 infinity and half plane. So this cuts x at 1, cut y at infinity, and cut z at half. So from the origin, this is x and this is completely 1. It cuts y at infinity, which means it does not exist, so there is no y term there, and it cuts z at half. So if from here to here is 1, it means half is somewhere around the middle, 1 over 2 in z. So join x and z together and we'll have something like this. Okay, but not also forgetting, if I call here to be my origin, I can call here what? X. From the origin to x is 1, and then from the origin to z, this is also z direction is half. So which means I can reproduce half here somewhere around the middle. So join these two as well together. So I've been able to reproduce what is down to up. So I can join all the points together, join all the points together. This becomes my plane. Okay, that becomes the 1 infinity and 1 plane. Next question says draw the or show the direction. So from the origin, draw a line which cuts any of the plane at 90 degrees. So I can draw this line from here. This cuts this plane at 90 degrees. So this can be my direction. Okay, let me take it out a bit. So I have this direction 1 infinity and 1 direction, and enclose it in a square bracket. So that's the first part of the question answered. So let's look at the B part of the question. So I'll take this camera back now to the other side. Let's look at the B part of the question. So the second part of the question says find the interplanar distance between two planes of Miller indices 321 and 102 with in a unit cell of 4.05 Armstrong unit lattice parameter, and also find the angle between the given directions 321 and 102. Okay, so let's do that over here. All right, so in the B part of the question, we are given the Miller indices 321 and 102. Okay, Miller indices we are given 3, 2, 1, and we are given 1, 0, 2, and we are asked to find the interplanar distances. So let's start with the interplanar distance of 3, 2, 1. Okay, so for 3, 2, 1, okay, the distance or the interplanar distance of 3, 2, 1 is equal to, remember the formula we gave in the previous video, we simply says it is the lattice parameter or the lattice constant all over the sum of the squares of the given planes, h squared plus k squared plus l squared. Okay, so we have 3 stands for h, 2 stands for k, and l stands for 1 in this case. So we're given the value of the lattice parameter. Recall, a was given to us from the question. A, or lattice parameter A was given as 4.05 Armstrong units. Okay, let me just confirm. Yeah, it's correct. 4.05 Armstrong units. All right, so the lattice parameter is expressed in Armstrong units. We have 4.05 Armstrong units. All right, so it depends on your mode of conversion in any country you're watching from. But in my own part here, over my own part here, River State, Nigeria, we convert this to centimeter. And to convert lattice parameter to centimeter, or to convert the Armstrong unit to centimeter, you simply multiply by 10 to the power of minus 8. So therefore, it means that the lattice parameter A is equal to 4.05 multiplied by 10 to the power of minus 8 in centimeters. So this becomes the value of the lattice parameter. Now, calculating for the interplanar distances, therefore, for the first case now, D3, 2, 1 is now equal to, we said, Armstrong units, and the value is 4.05 by 10 to the power of minus 8 all over the square root of the sum of the squares of the individual Miller indices. So we have for h squared, which is 3 squared. So this becomes 3 squared plus k squared, which is 2 squared, okay, plus l squared, which is 1 squared. All right, so this is now equal to 4.05 by 10 to the power of minus 8 all over the square root of 3 squared is 9 plus 2 squared is 4 plus 1. Okay, this is 4.05 by 10 to the power of minus 8 all over the square root of 9 plus 4 plus 1 gives us 14. So the interplanar distance between the 3, 2, 1 plane is now equal to 4.05 by 10 to the power of minus 8 divides. Now we obtain the square root of 14, and the square root of 14 is 3.63 is 3.7417. So we have 3.7417. So this 4.05 exponential minus 8 divides 3.7417 gives us the interplanar distance between the 321 plane Miller indices, and the value is equal to 3.63 by 10 to the power of minus 4 in centimeter. All right. So that becomes the value of the interplanar distance for that given plane. Next, we find the interplanar distance for the second plane. Second plane is the 102 plane. Same thing. D102 is equal to the lattice constant all over the square root of the sum of the squares of the plane. So we have h squared plus k squared plus l squared. So this is equal to, the lattice parameter is constant, remains 4.05 by 10 to the power of minus 8 all over the square root of, now h squared becomes, h here is 1, so you have 1 squared plus k squared, k here is 0, okay, 0 squared plus l squared, l here is 2, you have 2 all squared. D102 is now equal to 4.05 by 10 to the power of minus 8 all over the square root of, okay, so 2 squared, 1 squared is 1 plus 0 squared is of 0, 2 squared is 4, so you have this. So this is equal to 4.05 by 10 to the power of minus 8 all over 1 plus 4 is 5, so you have square root of 5. So let's obtain root 5. D102 is now equal to 4.05 by 10 to the power of minus 8 all over the square root of 5 is 2.2361. All right, so from here we can now find 4.05 exponential minus 8 divides 2.2361. That gives us 5.918 by 10 to the power of minus 4 in centimeters. So this becomes the answer to that interplanar distances. All right. So the second part of the question says we should find the angles between the directions 321 and 102. Okay, so next thing is to find the angle between those directions. And we've already outlined the formula in the previous video on how to find angles between given planes or given directions. All right, so okay, so let's put down those directions now. We have the direction 3, 2, 1, and of course you have 1, 0, 2, and we are asked to find the angle between these directions. So I said in the previous video that cos theta is equal to angle between two directions is simply, we said h1 h2 plus k1 k2 plus L1, L2 all over the square root of the first plane, H1 all squared plus K1 all squared plus L1 all squared plus the square root of the sum of the squares of the second plane, K2, H2, H2 all squared plus K2 all squared plus L2 all squared. So you simply have this. Therefore, cos theta is now equal to h1 stands for the value of h in the first plane. So this is h1, this is k1, and this is l1. Whereas this is h2, okay, this is k2, this is l2. All right, so h1 is obviously from here 3. You have 3 multiplying by h2, and h2 here is 1. So this is 3 times 1 plus next we have k1 times k2. K1 here is 2. So I have 2 multiplied by k2 here is 0. So 2 multiply 0 plus I have L1, L2. L1 here is 1. So this is 1 multiplied by L2 here is 2. So 1 multiplied by 2 all over. So we have the square root of the squares of the first plane. We have there 3 all squared plus 2 all squared plus 1 all squared for the first plane. Okay, plus the square root of the second plane. We have square root of the sum of the squares of the second plane. We have 1 all squared plus 0 all squared plus 2 all squared. Okay, so cos theta is equal to 3 times 1 is obviously 3, okay, plus 2 times 0 here is 0, plus 1 times 2 here is 2, all over, I have now square root of 3 squared is 9, plus 2 squared is 4, so 9 plus 4 gives us 13, plus 1 squared, and 1 squared is 1, so 13 plus 1 gives us 14, so we have square root of 14 plus, similarly, 1 squared here is 1, plus 0 squared is off, okay, plus 2 squared, so 1 plus 2 squared is 4, that gives us root 5, so I have square root of 5. So this is equal to, now 3 plus 0 plus 2 will simply give me 5 all over root 14 plus root 5, root 14. Root 14 gave me 3.74, okay, plus root 5, and root 5 gave me 2.24, 2.24, okay, so I have this, and this is equal to 5 all over 3.74 plus 2.24. That gives me 5.98. So we simply find, okay, so this simply implies that cos theta is equal to 5 all over 5.98. So we simply divide 5 by 5.98 and this will imply that cos theta is equal to 5 divides 5.98. That gives me 0.8361, and therefore the angle is now the cos inverse of 0.8361. So simply taking the arc cos of this value, we can now obtain the angle to be equal to cos inverse of 0.8361 will give me approximately 33 degrees. So it becomes the angle between the two planes, 33 degrees. So that's it, guys, on how to find interplanar distance and angle between planes. I hope you find this video very interesting and helpful. Please, if you do, I would like to get your thoughts in the comment section. And of course, if you're new to the channel, do well to hit the subscribe button to keep getting updates when content such as this keeps dropping. In the next video, we are going to be talking about crystal structure, simple unit cells, face-centered cubic, body-centered cubic, and how to find their atomic packing factor. I will see you in that video. Thanks and cheers.